In this video, let's talk about event-driven simulation. The reason for event-driven simulation is the time-driven simulation fundamentally is not efficient and accurate. As we see, an event in a time space is actually a dot. If you, at any time and space, you observe, most likely you find nothing. Only at some small areas, at some discrete points, you will find an event happening. So if you use time-driven, each simulation cycle, you advance a small amount of time. Like here, you check 1, 2, 3, 4, 5. At the fifth circle, you hit an event and you update your picture. As you see, the first 4 checks observed nothing, and it's basically a waste of your cycle. More serious than waste of CPU cycle, time-driven is not accurate. As you continue observing, 1, 2, 3, 4, 5, at fifth, it observed nothing yet. Next step, no matter how small it is, it's still a time interval. There are chances the next observing find nothing too. And between two observings, an event just happened without your notice. So time-driven simulation is not accurate in that sense. How about we change strategy? We do event-driven, like we only take action when there are events happening, and we do nothing in those areas. In the real world, it's impossible, but in computer world, it's possible because in the simulation world, we know the exact projection of the two particles. We know their time and position in the future, and we can predict when two particles will hit each other with the name of mathematics. And we only update our graph. We only do our calculation when at the time the two particles collide. So we only observe here and do nothing in those areas when nothing happens. So next question is, 2 particles is easy. How about 100 particles and 1,000 particles? How we deal with their interactions? The answer is simple. We only have to deal with 2 particles at a time because we know priority. Say tomorrow you have 100 events to deal with, and it's kind of overwhelming, so you write a priority queue and deal with the most urgent event at the top. Once that event is solved, the situation might change. The next 99 events might be easy to deal with, and after you burning down the first 50% of the events, the rest of the events might luckily just disappeared. And you see the nature. When you deal with one event, the other event changes. And also it could be possible a more urgent event comes in and gets the top of the priority queue, while you are dealing with the first event. So that's philosophy. Let's write code. The interesting part. Okay, so in order to simulate a collision system, like we have many particles, they collide each other. We only calculate and redraw the stage when there are collision happen. And just like this, in theory, event-driven is most effective because we only take action at this line and this line and do nothing in those lines. But for time-driven, you need to constantly checking, in the risk of missing something. Okay, here in the center of the event queue is a priority, and the events are ordered by their priorities. So let's see. I cannot go to the event. Okay, the event is representing when two particles collide, and they are ordered by the time in the future. The most urgent event is get more weight. So when one event happens, we will take actions, either update the state of A and B, or draw a picture, say like that. So we have a priority queue, and then we can deal with only one particle at a time, say one event at a time. And here we can predict, give me a particle, and we can iterate through all its neighbors and calculate when they will hit with a neighbor. And when we find the next event, next collision, we put that event into the priority queue. And the most urgent event will get to the top, and unurgent event, like happening 20 years later, we don't even care about, because we only care about 10 seconds in the near future. 20 years, we don't put it into our priority list. Let the future take care of itself. And of course, we also need to take care of hitting the wall. In that case, we put the B or A as null to signal this is a wall hitting instead of particle collide. Now we can predict. Once we can predict, we can simulate. Given a priority queue, we iterate through the particles, calculate their collision with their neighbor, and in order to fill the priority queue. Of course, we artificially generated an event with both particles as null. This is signal the computer. Once you see this kind of event, you redraw the stage. So artificially, we have three kind of events. Event 1, two particles collide. Event 2, particle collide with a wall. Third one, artificially, computer draw the picture. So those three kind of events are interleaving, and we need to deal with them one at a time. Okay, here this is a while loop. We get the highest priority event, and we examine what's in that event. Find the two parties involved in that collision. Since this is the highest priority event that happens at the nearest feature, so we know at the time that event happens, there's no other collision happens before that. So we can advance all the particle with that small time interval, knowing that we only have one collision happens at this time. So that one collision, either it's bouncing off each other or bouncing on a wall, or it's time to redraw. And we deal with that event, either update A and or B's velocity, or we draw the picture. And at that point, the event happens. A and B's state changes, and we need to update the rest of the word. Say the 99 events in your priority list. At that point, the word is divided to two parts. One part is A and B, which just changed their state. The other is the rest of the word which didn't change their state yet. They are on their projection to the next condition. If A and B not get on their way, they might just see nothing between this moment and their next condition. So what we need to adjust is we should calculate the next condition of A and the rest of the word, put them into the priority queue, see if they will change anything. The same as B. So the cycle is like this. We get the highest priority event, deal with it, then adjust the rest of the word according to the new state of A and B. And we cycle again, get the next event, deal with it, adjust, then next one, deal, adjust. And the word continues forever, like in this scenario. And here is a main loop. We have an array of particles. We randomize their position and velocity. And we simulate, only care about the first 10 seconds, only care about the events happening in the next 10 seconds. And forget about the events happening later. And we have two helper classes. This one is draw the graph. And not very interesting. It's basically a JFrame with a buffered image. And when we try to clear, we just draw a big square and cover the existing picture. When we try to draw a particle, we just add some circles to the existing graph. When we show, we do a repaint. And here is a particle from the physics course. A particle have a position, velocity, radius, and a mass. And they can move during a time interval. And we can calculate when they will collide with the next particle or collide with the walls. When they are bouncing, they change their velocity. And that's it. We run the program. It's bouncing. We only update the we only do the calculation when the collide happens and do nothing between collides. And just for fun, let's change physics. Each time the particle bouncing on the wall, they lost some energy. So eventually they will stop. And Vy. Okay, let's run the program again. As you can see, each time when they're bouncing on the wall, they get slower, and as a whole, those particles running slower and slower. That is exactly what happens uh, in a, say, in a room, a hot room. Particles bouncing on your wall and they lost energy. If you don't input energy, your house get colder and colder and eventually freezing. Okay, and just for fun. This is an event-driven simulation.